to put it in your mind. This is the history of DNA, and if you look at it, it started in 1910. That's very early, huh? بس يعني مو قبل 500 سنة 700 سنة قبل 100 سنة. We did not know genes وما قالت until about 1944. Gene theory 910, but it was still fuzzy. Until 1944, then we start talking about DNA, RNA. This is very early. I was born in 1952, so this is 1 year after I was born. Was Cyril Crick discovered DNA. So this is a very young-ish science. Very young science. This is the paper which they wrote, how to win a Nobel Prize. He wrote one paper, 1.5 pages, and they won Nobel Prize in science and later on in medicine. Amazing, huh? 1 page. I told you about him. Yeah? And I told you how our variation has to be diversity, how it is. This is what is known the future of medicine. It is started by being called individualized medicine. Now the name has changed to personalized medicine. Now the chain has changed again to precision medicine. And what do you mean by precision medicine? We mean you have to deal with the person in medicine according to his genetic profile. According to what? To his genes. Basically, personalized medicine, سميه الآن precision medicine, refer to using information about a person's genetic makeup to tailor strategies to treat his disease. So now, meaning I cannot give you the same medicine. I have to find out about your age, genetic makeup, before I can do that. And he tell me, is it happening? It is happening. It's happening even here. I started it. Enormous success in medicine we have. Medicine had an enormous success. Average lifespan in 1900 was about 40 years. Now, average lifespan is age around 70. You understand? So that's mean age, increasing survival, increasing life of a person. This is enormous success, practically double. Improve the quality of life. Look at me. I'm over 50. I'm still working. People at that time, by the age of 40, hey, they work the phone. This is incredible. So we had incredible success in medicine. Like, is that very good, or do we still have a problem? We have a problem. Many diseases with increasing incidence. Tell me one. Cardiovascular. Tell me one. Diabetes. We're having a problem. Diabetes until 20, 30, until 50 years ago, nobody even knew about it. Very few people who had diabetes. Now, out of 5, 4-5 مليون يعيش فوق العمر 50، 3 منهم يعيشون ايش؟ Diabetic. So we have an increasing prevalence of diseases which we didn't know. Unacceptable frequency of adverse events. Give him a drug, you think he's going to be better? يجيك جثة. You understand? Adverse effect, we don't know. And طبعا ايش increases? Expensive. Now, sickle cell anemia, we just now, 2 months ago, we discovered, or there is a new treatment for sickle cell anemia, and that is by stem cell. Huh? They take a stem cell and play around with the gene, with CRISPR, and put the new gene, and now sickle cell anemia are completely cured. That costs per person $2 million. How many people have $2 million to pay? Increases expenses. So we still have a problem. Now, incidence increasing throughout the industrialized world, diabetes. And it is associated with obesity. The more obese, the more rate of type 2 diabetes. A lot of children, can you look at children? I walk and I look at children. Practically 3 out of 5 are obese. Are obese, even though they are aged twiddlers, very small, young. Chronic illness with an array of complications. Diabetes, not فقط sugar, it affects the liver, it affects the kidney, it affects the heart, it affects the blood, it affects multi-system problem, micro and macrovascular. So it has a huge consequences. So now, if you have one member of your family developed type 2 diabetes, listen to this. Would you like to know the prognosis and the response to existing treatment for the average patient? تروح للدكتور يقول له الله يخليك ايش تعطي انت بقية الدايابيتس؟ صحيح ولا لا؟ قدني نفس الشيء ونعطيه اعطيه. You understand؟ مينك ايش؟ دواء لكل الناس، نفس الدواء لكل الناس. Would you like to know? I would like to know. I would like to know what's happened. But then, or would you like to know as precisely as possible the specific features, prognosis, and response to therapy for your loved one? ما دام تعدل لي بالتفصيل شو حيصير؟ زين هو كيف يقدر يقول لك بالتفصيل ما يعرف عنك شيء؟ You understand? Or even better, would you like to know ahead of time, assuming there are preventive strategies for the disease? ما شاء الله الأفضل أصلا أمنعه أنه ما يصير فيه. These are all now available. We can predict. So what medicine you're going to practice is that the last one, not the first one. Why? Many reasons. Average medicine for the average patient. The classical case of mentality. خلاص هذا صار بيزين أعطيك ثاني هذا ما راح يصير فيه زين. ها؟ راح يتعالج فيه. هذا المنتاليتي which we have. Taylor, try and error في الميديسين. أعطيه هذا. تعال لي بعد أسبوع. إذا ما صار شيء دكتور أخذ هذا. بعد أسبوع تعال. Trial and error until you find one medicine. You don't know that previous medicine could have probably killed him or destroyed or damaged. And that's what we're doing now. A trial and error. We keep changing the medicine until we find the one which suits that person.
Isn't most medicine right now trial and error?
Trial and error, that's what we do now. What we practice now. You know? وجعات أعطيك بنادول ما صار أعطيك سوفتين ما صار أعطيك. You understand? Without knowing what damage that drug which I gave you has done. Possibly treatment, sequential, until you find the one which works. But that previous one could have caused age, could have caused problem. This Tonkin, 1963, is a big known physician in his time. He said, there is no science of individual. Listen to this. No science of individual. And medicine suffers from fundamental contradiction. There is a contradiction in the way we practice medicine. What is it? If the practice deals with the individual, while the theory graduates the universe, while the treatment is for every person on earth. And that is contradiction. You're treating them. You're not treating the universe. And you think this is old age? Listen to this. This is Aristotle, huh? 350 years before Christ. يعني ايش 350 الان 2000 وكم احنا 2000 يعني 2500 سنه 2400 سنه. The doctor does not treat man except accidentally, except by chance, trial and error. He treats Callus or Socrates or someone else. So if someone knows the universe without knowing the individual contained in it, he will often fail in his treatment. For it is the individual who has to be treated. Okay? He talks about individualized medicine, precision medicine, 2500 سنة قبل. You see this man? You see how brain works? I'm talking about it now 2,500 years, talking about what he said 2,500 years ago. That you should treat the man, not the... If you look at these children from far away, all look age the same. صحيح ولا؟ All look children, all look the same. Each of these individuals has his own unique sample of our species genetic endowment. كل واحد has his own genetic profile, different to age to the other. Unique history in the individual development. When he was in his mother womb, depends what the mother eats, what the mother does, what the mother smokes, but different, each one. So he must have been affected age differently. Family with its unique constellation. This family, we have all the same constellation of age, of genetic endowment. So we are different. And therefore we will respond age differently. Response. One of the major drugs used in the world is a statin. This is similar statin. There are many types of statin. I use rosuvastatin. You understand? Rosuvastatin, simvastatin, pravastatin, magnesh, many kinds. This lowers age blood cholesterol level. And look at the people. Look at the people who respond. Some do not respond. Some respond. Some over-respond. Different. Will you give this one the same dose as this one? Even the same drug? It's not the same dose. Why he has this and why this guy has this? So we are not the same. What changed? What has changed, which now I am telling you, you could start practicing age precision medicine. First, Human Genome Project. 2007, the first human map of all genes, of all chromosomes, was announced. So I know now the human genome sequence. Before 2007, we didn't know. It started in 1998. You know the story? You know Reagan? Anybody heard of Reagan? Ronald Reagan, the president of the United States during the 80s, 1980 to 1988. They came and told him, he said, I want something for people who will remember me by. So his advisors went, and a week, 2 weeks later, they came, we found two things. He said we could build one aircraft carrier, and call it Ronald Reagan aircraft carrier. Okay, what is that? The others, he said, we could sequence the human genome. Sequence? What is it? Sequence the human genome? So what is it? So they told me what is the whole thing is all about. They told him, so he asked, how much is the carrier? How much is each aircraft carrier cost? $14 billion. And how much is the human genome cost? $14 billion. And how long it takes to build an aircraft carrier? قالوا لها 10 سنين. So how long it take to do sequencing? قالوا لها 10 سنين. راح فكر ثاني يجي قال he started the movement كل العالم كله China, America, Russia, Germany كلهم أخذوا كل واحد أخذ كروموسوم قطعة من الجينوم and they start sequencing and the sequence is the genome. 2007 the first map of the genome was published. Whole genome sequencing, biology. So we start learning how to sequence faster and faster and faster. Increasing prominence of evolutionary thinking. Now evolution مش معناها Darwin, no, we start thinking evolutionary. So we could trace and explain the genes with diseases. Disease gene identification, we start identifying association of this gene with this disease. هذا كله 2007. Individual genome sequencing. At the time, I get my blood and I had all my genome sequenced. I know exactly what my genome looks like. I know exactly what I respond to. I know exactly what I don't respond to. I know exactly what I am at risk of. You understand? I know exactly which drug I respond to, which drug I don't respond to. I know everything. I have only one thing I don't know. If I know how tall is my telomere, if they could do that for me, which they didn't do, I can tell when I'm going to die. You know everything about your body. There's nothing now which we don't know about our age, our body. This is the gene, exon, intron. We're showing you that. When the sequencing is started after 2007, for people you could ask, it cost about $10,000 per genome. It cost 17 billion to sequence one genome. But then, after about a couple of years, it became 10,000 because our technology went extremely fast. And the cost came down. Look at it. Now, you could do by $1,000. You could do sequencing, the whole genome, but I did it $4,000. Now it could cost probably $1,000. Cost you to do a whole genome sequence. This is exactly the opposite to what Moore's law is. Moore's law tells you that's how the price, the cost should do. The cost after so many years should have gone down to where? To that area. But look where it came down to. Because we have a technology, incredible technology, which gave us the chance to be able to do this at a far, far lower prices. Now, I have many genomes, not mine, many genomes of the diseases which I work through on people, cardiovascular, breast cancer, diabetes, كلها I have to store the information in the cloud because I don't have, this is trillion and trillion bytes. So I don't have computer to take this. Terabytes, I'm talking millions and millions of terabytes. I'm putting it on the cloud. Now the cloud, storing it, costing me more than the sequencing. That's how cheap sequencing now is becoming. Look at this. A woman, age 37, presented with stage 2 estrogen receptor positive breast cancer. Breast cancer يقولون estrogen positive, progesterone positive, HER positive or negative. This is how we classify them. You will understand that later. Estrogen receptor positive breast cancer. She is treated with surgery, chemotherapy and radiation. She was, how old she was? 2 years later, she came back. Stage 3, ovarian cancer. Again, she was treated with surgery and chemotherapy. تفضلي واحد بيتكم. 3 years later, at the age of 42, she comes back with more ovarian and more chemotherapy. هاي ثالث مرة. رابع مرة 6 months later, she comes back with acute myeloid leukemia, blood cancer, AML, and this is acute, sudden. She goes into respiratory failure and dies days later. Why? Because we're giving her the same treatment we give everybody else. We don't know about her specification, her genetic profile. So now, that's what we're going to from genetic, gene, mutation, to genomic, whole genome, polymorphism. We use the whole genome to get to know about a patient case. Not a genetic one gene, no. DNA sequencing, are we all the same? 99.6% identical. كل الناس. I'm identical with you in 99.6% of our DNA. So I mean we differ in age. We differ in only 0.4%, which is about 3 million SNP. Look at it. I even age identical to the mouse and identical to the chimpanzee. So we are identical. But this difference is the one which makes the difference. Look, how many genes we have? 22,000. How much the mouse had? 22,000. 75% of them we know. 75% of the gene we know. But the one we know in the human, we've got to know in the age in the mouse, or vice versa. Exon, 8.5% exon, that's 8.4% of the age of the exome is the coding region. Total exome, 220,000 exome. This is 210,000, not much. Exome 50% megabytes, that one is not much base pair, and that's not much different. They're very similar. What is the difference between me and you? And what's the difference? Is it because of insertion, deletion, insertion of base or deletion of base that only constitute 10%? This is known as indel. The difference between you only in 10%. Is it length of polymorphism, short tandem repeat, STR? This is only constitute 5%, the difference between me and you, and between you and your friend. Is it SNP, single nuclear polymorphism, the one which I talked about? Look at it. We differ in 45%. That's the big age difference. That's what makes me genetically profile different to age to you. Look at the CMV, copy number variant. I have 1 copy of gene, you have 2 copies, 3 copies, 4 copies, and so on. Look at that. 40% different. So we differ in where? If I ask you, tell me, what we differ in? Do we differ, if I want to know how different I mean to you, should I count it insertion, deletion, STR, or SNPs? And copy number. These are the one I use. Copy number and SNP, single nucleotide polymorphism. Conversion, not much. Single nucleotide, Q to G. This is just a simple one. The frequency in 1 in 1,000. Current SNP genotyping could tell you up to about 1 million. Now, actually, this is 10 years ago. Now we have chip which could count up to 5 million SNPs different between me and you. Copy number, I have 1 gene deleted. Here I have a duplication. Are we the same? Are we the same? We're not the same. Expose, dosage, sensitivity. You are sensitive to this drug. I am not sensitive to this drug. For deletion, exposure, otherwise, normal variation remaining allele. Create fusion genes, which results in cancer. Let's have a look. Look at this one. The difference between him and him, 1 in 1,000. That's all. 1 in 1,000 different. Made him short and made him so tall. In Neanderthal, you understand? I differ from him. Differ in what? Not the number of genes, look. Energy metabolism. Genes involved in energy metabolism. Because obviously what he eats and what he does different to what I am doing and eating. Now, cognition. I am far more cleverer than him. understand? So genes responsible for cognition, we are different. Neurodevelopmental, which is result in cognition, you understand? We also differ. Or in microRNAs, these are the ones which controls the genes. We differ as well. I have far more complicated microRNA than the mouse. So for Neanderthal, we probably even more. So we differ in genes, genetic profile. How did we come up with all this? We did what is known as genome-wide association studies. This is a type of study. Genome-wide association study is a type of study. It is agnostic. Can you see? Agnostic approach to identify SNP. Agnostic يعني هذا اللي يؤمن بالله بس ما يؤمن بالأديان. فهمتني؟ Agnostic means يؤمن بالله بس ما يؤمن بالأديان. Meaning ايش؟ Meaning blindly. I didn't go to look for a gene which is associated with diabetes. No. I look for any gene which is associated with diabetes. This is what we mean by genome-wide identification of causative variant and linkage disequilibrium, meaning different in one family or in one population than other. You know. Understand pathophysiology increases that. For example, look at this. There's a chip, and on it there is the 1 million or 5 million SNP. كلها robotic. It amplifies DNA, and then you add it to the chip, and the chip tells you which SNP you have, which SNP you don't have. So it's very easy done. That's what we do. This is known as microarray. You understand? SNP genotyping. This is what we do with genome-wide association study. Use a microarray. So what we take? We take patient and we take healthy people. And use the same chip. And then identify the SNPs which are in these people and identify the SNPs which are in these people from this. You know, this is the chip, gives you colors. But you don't read it. Computer read that, you know. And then you get the following. You get the following. If you take cases, controls, individual discovery studies, or individual discovery study with SNP2, SNP1. This is a SNP1. This is a SNP2. This is كل واحد من ايش is a SNP. And you look at it, they're all the same in both patient and control. معنى ايش؟ معنى the difference is not really significant. This is known as the Manhattan plot. Manhattan is ايش؟ New York. When you come to New York from far away, you look and you look كل البلدين حوالي 30 40 ايش؟ طابق. كلها straight. لكن شوف واحدة ايش؟ هذه. This one. اللي هي Empire State Building, ها؟ شو عادي؟ تختلف. Meaning ايش؟ This is significant in patient compared to mean. Compared to mean to normal. So if I go to you now, or I go to somebody else and take the blood and say, this is SNP. Forget all the others now. I look just for this is SNP. And I saw your hand. Oh, you must be at a higher risk of developing the disease if it was cardiovascular disease than age. This is what we know by genome-wide association study. And this is how we do the studies. Up to now, there are hundreds and hundreds of SNPs which are associated in various chromosomes, which are associated with diseases. And we could do that for every person, very cheap, costs only about 100 riyal to do the snipping. Not sequencing, this is a snipping. So if you look, 1,500 GWAS has been conducted in the world. I added another 3 to it. 952 cases with controls, well, there are far, far more now. Now, they're done in 18,000 and 19,000. Disease case control study, meaning gene, disease association, look at it. Majority is qualitative trade, meaning a phenotype is right, and then pharmacogenetic, meaning drugs. Your response to the drug study. Breast cancer, relative risk is 1 for the population. If you are alcohol consumer, it goes age. Risk is become age higher to the genes. If you are obese, risk goes age higher. First degree relative with the breast cancer goes even age, which is that higher. And first degree relative below 50. This is all from the genes which we understood. We could tell now the risk for age for breast cancer in every patient. معنى I could stop it, صحيح ولا لا? I could stop it before it is age. It happened. Number of gene breast cancer, 25. Publication, how many genes? 57. Now it reached 100. Many. طبعا some of them are common in all the population of the world, and some of them are rare. Rare meaning only in families or specific population. And so on with all other cancers. And you see, we can tell that. So we can tell the gene, we can tell the mutation. So shouldn't you do that for a breast cancer patient? See what gene she has, we can do that now. And we can tell if she has higher risk or no risk. So from single gene to genomic to concept. This is a picture of sequencing. When you do sequencing on the machine, it tells you C, A, L, C, and so on. Understand? Tell you the sequence. This is an output from the machine, but the machine which we didn't tell me if there is any difference. How we do sequencing, or next generation sequencing, the whole genome, we break it into 350 to 500 base pair, length, capture it of interest, the area of interest. We could do that by different methods, by having something which is attached to it, amplify, attach, bind, proceed, and then amplify it, and then we start sequencing it by synthesis. We synth one by one, and we find out what is the sequence of that. It is not complicated. The theory is supposed to be very simple, you understand, rather than complicated. But this is all done by machine. This is the machine which we have in our lab. In the center, I bought it. It's called HiSeq, which Illumina, which does all the sequence. You put the machine and it does it to you. Properties of next generation sequencing is that, can you see this chip? This is a chip like, and you bind it, and then on that chip you do it. So it is all machinized, you understand? You don't do anything with your hand. This is a small hole, but in it there is 1 million bases. 1 million bases where it could attach. So you could do a fast sequencing compared to the old time, which known as standard sequencing. So it took about 10 years to do the first genome sequencing. Now it takes about, in a good machine, it takes about 12 hours to do the whole genome sequencing. Nanopool, Oxford Nanopool, is trying to make a machine which is the size of a hand, which can do you in 1 hour. So now they're talking about clinician. You got a doctor, they give you a machine of this size, the patient comes, you tell him, just put your fingers here, from the soles of your finger, you take this out, then you come back 1 hour. 1 hour later, you have everything you need to know. The doctor has everything you need to know about your genes. This is where you have a precision medicine occur. So we have a massive capacity in increasing of sequencing. من بقول لك طلعت 10 سنين إلى كم؟ إلى 12 ساعة صارت. We have 500 gigabyte per run, and we could run like very easy, very fast. Cost used to be 10,000, now 1,000. So everything going toward $100 genome sequencing. They think by next year, the genome sequencing using that nanopool, it costs only $100, which is very, remember at the beginning, what it would cost? It costs only $100. So it is available to every patient. So what is the difference between sequencing and next generation? Provide this information to a small number of individual families, to the families. Likely only rare mutations still to be found. And you use this for rare mutation, not common mutation. Common mutation already been found out. Currently account for modest proportion of familial incidence. They use it mainly in families, you understand, genotyping. Potential for incident finding is high. You could find rare one, which is high, highly personalized, but rarity makes it hard to give a precise interpretation, especially if it is very, very rare SNP. You understand? And this is also very popular, very potent as well, like the whole exome, whole genome sequencing. But it takes a huge number to be able to interpret it. So can't provide this information for everybody. Common variant only limited by power of studies, meaning by how many patients you put. The more you put, the better you could get interpretation. Currently account for modest proportion, the same, highly personalized, but interpret in large groups. In this, you could use 200, 300 people. In this, you have to take a lot more patients. So personalized medicine is you find out disease susceptibility, responses to age, to treatment. That's what we use these kits, these sequencing for. So risk modification, if you know disease susceptibility, you could modify his risk. If you're telling him you have a problem with cholesterol, therefore do not take this cholesterol, take this drug, so you could modify it. Screening, public health, prevention, who has it, who doesn't have the gene, the mutation, disease classification, cancer, it comes to me, I want to know what the stage that cancer is, stage 1, stage 2, all based on the genes we could do, and pharmacogenetics, whether this drug, will you respond to this drug in a normal way, or in a substitution way, or in a higher way. So I can now specify the drug for you according to your age, according to your gene. مو فقط type, even the dose, according to your genes. So if you see the drug, you will see that 4 types. Drug which is toxic but beneficial to a certain group. It's toxic and is beneficial, but like in toxic. Drug toxic but not the benefit when of the high toxic. And see if some group drug not toxic but not لما تاخذه هو نفس الشيء. Drug not toxic and for example that drug I would give it to this group. I will not give it to the other group because it is toxic. So which drugs? Look at that. Cytochrome P450. This is the major gene which makes the major enzyme for metabolism of 25% of all drugs you take. Not all the drugs can have an effect. 25% of them have to be metabolized. And this responsible for 25% of the drug. No, people have a mutation which lead to this gene not working. So 6 to 10% of Caucasian carry no, meaning not functioning. 70 variant alleles, so it's a big difference. Ultra-rapid metabolizers have up to 13 copies of that gene. So there is difference in pharmacogenetics. CYP-TB6, poor metabolizers have about 50% to 50 to 1,000 times less. Intermediate, 5 to 400 times less. Extensive metabolizers are usually the one are normal, and ultra-rapid metabolizers are 4 times more than normal. So different people have different phase of metabolization. Hard to reach therapeutic level. I am I had the thyroid. You know thyroid? I had the thyroid actually. What thyroid does? What it makes? Thyroxine. Thyroxine. You understand? So I have to start taking a thyroxine. It's been 6 months. I cannot get the dosage right. Every time I think I got it right, I go and measure. There's a test for it. We see it is wrong. And it takes 2 months. So I 2 months, wait 2 months, take the same dose, do the test, find out if it's right or not right. If it's not right, I go change the dose and take it for another age, 2 months, and find out, look, this is my 3rd time. I hope 3rd time lucky. You understand? I know whether it is work or not it is, because my mood changes. Yeah? If you see me upset, it means this is not working. If you see me happy, this is probably overworking. It's very difficult to get the dose right for a patient. Even the same, because we differ genetically. Look at the drugs. Beta blockers. What beta blockers for? Heart. 60% young people. The drugs have to be aged. Metabolite, tricyclic, antidepressant. نص البلد depressed. صحيح ولا لا؟ paroxetine وماغاسيلاتيف سيروتونين ابتيك. mood. anti psychotic. نص الشعب psychotic. صحيح؟ شو بالسيارات؟ إذا تقولي دول مو psychotic يطلعك ويسيع عليك يشتم فيك. هو طالع عليك مش انت. كودين, amphetamine, tamoxifen, that for breast cancer. كلياتها has to be metabolized. This is very important drugs. These are the drugs which are dispensed every day in our hospitals. And they have to be aged, metabolized. Metabolized by me, by genes. And therefore we need to know, do you have the right gene? Or do you have a defective gene? Look at this. 60-year-old man diagnosed with metastatic esophageal cancer. So esophageal cancer was initially underwent cytotoxic chemotherapy, which is the usual standard care for this type of. This is the normal one. Give it to him. However, genomic analysis, when they did the genomic analysis of the tumor, identified a mutation in BCR-ABL kinase. BCR-ABL kinase, this is a fusion gene. This is a gene which causes leukemia. You understand? This is known as Philadelphia. So, this has to do with leukemia. Leukemia responds to imatinib. So he thought, not the imatinib. You understand? Nobody will tell me you're crazy. No? You're stupid, you shoot, not the imatinib. You would never think of giving Glivix, imatinib, for an esophageal tumor. Dr. Bakusi said, but the target that the drug is normally effective for was present, the man's particular tumor. It was an incidental finding. By incidental finding, I think there might be become additional identifier. And he did give it to him, and he was treated. If we didn't have genomic, can we treat him? Because nobody thinks to give imatinib to somebody with esophageal. Imatinib is leukemia. MLA. A patient presented with rare tongue adenocarcinoma and no standard treatment option. Nothing option. You don't have for that time. The tumor showed elevated EGFR, growth factor receptor. This is in rare breast cancer. EGFR and breast cancer. The tumor showed elevated EGFR, but the treatment with the EGFR inhibitor, which is erlotinib, did not slow down the tumor. So, خلينا نسوي له sequencing. عنده فلوس في ذاك الوقت سوى له sequencing. Identify mutation in other genes that override the allotment. And they start treating him with that, sanitary, and use the pesticide for other sort of carcinoma, not that type of carcinoma. The first treatment stabilized tumor growth for 4 months. When the cancer spread again, they used another RIT inhibitor and anti-inflammatory agent, sorafenib, which stabilized the disease for 4 additional months. Analysis of the recurrent tumor showed that there are so many mutations in the tumor he had that you had to go for each one. This is what is known as precision medicine. Otherwise, you will end up by error and trial. Do you have controversy in precision medicine? Yes, we have a controversy. DNA banking and research. Start looking for DNA, and I look into Fulan and I find something. This DNA belongs to that man. Should I tell him or shouldn't I tell him? He didn't tell me to do that. I did it for research. And usually when I go to research, I don't know who's who. But I found. Do I have the right to keep quiet? Or do I have the right to go and tell him? Controversy. Or am I using, this is DNA, I had a DNA man, Einstein. You understand? And you know Einstein is very clever. And these are the genes which are for cleverness. Should I extract them and put them in another cell and see what's happening? You're playing God now. Design babies, that's what I mean. You design all in babies. تجيد طبعا. ها؟ كذا أنا عندي جين وبيع جيناتنا. You understand? So the baby comes exactly how the mother and the father wants them. Controversy or not? Controversy. Reproductive cloning. انولد الطفل اخذ some of his stem cell من الايش؟ من cord blood or the placenta cord blood اخذ stem cell ضمن يكبر الولد يصير بيه ايش؟ اعرف انه راح يصير بيه heart problem and you need a heart. Grow these cells. Grow it in the lab and make another baby and take the heart of that baby and give it to this one. You can do that. Easy. They did it in the Kharfan, Dolly. If they could do it with Kharfan, could you do it for a human? A human مش يختلف كثير عن الخرفان. بعض الhuman are خرفان. Embryonic stem cell. You could do anything we want. From embryonic stem cell, you could do anything. You could make one, a human, and cut him into pieces, keep his heart, his kidneys, his liver, his lungs, and even its storage. And they could nitrogen in the air, in the fridge. You could do that now. You could do that now. But it is ethically illegal. Your challenge, so as a doctor, your challenge is to understand the science and the ethical issues. Because you're going to do some research. And واحد منكم ما يتطخ براسه انه يسوي كده. You need to understand that. Support informed decision. A woman comes and her breast cancer. تقول لي سوي هاي الطفلة ماتي عمرها 6 سنين 7 سنين. That she has the same gene. What are you going to do? إذا تعطيني فلوس سوي معي. صحيح ولا لا؟ But do you think that's ethically? Will you do it or wouldn't you do it? Would you do it or wouldn't you do it? No? وإذا أعطيتك مليون ريال شوف سكتك يعني probably don't. في ناس يسووا بقل. You understand? And that is an ethical problem. Imagine you find that girl, 6-year-old, has a mutation. What are you going to do? What are you going to do? What are you going to do? 6 years? You have no right to do anything to her. You understand? So there are ethical controversies. Support informed consent to support those with the special needs, those people who don't have the knowledge. You have to support them, to engage and stimulate community debate. How many of you did research? Nothing. Nobody. You want to do research? Couldn't someone research? Huh? I advise you. Go to the people, general population, in the village, in the city, yeah, and tell them, what do you think about age? About sensor. Do you think should we use it? Shouldn't we use it? Should we ask? That's a research. That will tell you what your community is going to tell you. Go to the religious one. Good Lord, I want to do this. What do you think? This is what research. This is how we get to age, to consensus. This is how we become knowledgeable and age ethical in doing age our work. Okay? Because then I take my approval from community. To help shape the people we become, that's what it does. How science genetic define مش بيكون حش على science وقال لك بالذوق كده كافر والحيد داروين استنى أنا ممكن مؤمن أكثر منك وأنا مؤمن أكثر منك. What is this? This is science. ربك أعطاني هالعقل وقال لي اشتغل فيها. قال لي اشتغل فيها الله. جاي من عندي أنا وجاي من الله. We need to have this type. And this type of community teaching does not come from somebody who doesn't know. It comes from who? From you. You understand? You might smile in the way I say it and joke, but this is your responsibility. You understand? To help people. This is one way of helping people. So you have to take this seriously and start thinking seriously. You understand? Don't take your job very easily. انت عندك مثل ما يقولون اشرف. ها؟ اشرف مهنة. So you have to act the same way. So what do? You have to do? Look, rigorous research. You need to do a lot of research. New technology, use it. Use the new technology. Don't leave it behind you. Will not be quick, but has already begun. Acute lymphatic leukemia. We've been aged. Look, 10 years ago, we said the disease, sickle cell, is going to be treated. It has happened now. This acute lymphocytic leukemia has happened. Imatinib has happened. This is when we taught our students. I taught my students 10 years ago that. Told them, that's what's going to happen. Contribute, do that. Well, they are now. So whatever we said now, probably even more. So you're going into this type of age of life, acting as age, acting as doctor. Doctors mean age, mean an honorable. You understand what honorable? Honorable profession. So you have to act honorable. I go in a place, everybody stands up. One. Stand up because of my profession. Same with you. You need to use that as a tool. That's when you become successful, by the way. ولا إذا كنت تلخبط راح. So you have to do all that. You understand? Exposes pitfalls. That's the thinking. You understand? How mistaking we do this and that, and tells you this is not really to me important, but this tells you what you need to do as a profession. المهم في النهاية I don't want you to be like him. He's a child who's slowly dying, and he's sitting and doesn't know what to do. That is the worst thing which could happen to a doctor. I'm talking about an honorable doctor. Inshallah, kulkum honorable doctors. You understand? That when I have no way of treating this patient, no. You are in precision medicine time. So you need to go حتى إذا الدكاترة قال لك لا فشلت تقول لا غصبا عنك I want to go into this. You understand? I want to do this, I want to do that. So you could save إيش؟ Save your patient. You know? And if you save patient فأعطيك فتوى هسه فتوى دينية. If you save patient I guarantee you جنة.